So today we're going to talk about 2008 AMC 10B problem 15. How many right triangles have integer leg lengths a and b and the hypotenuse of length b plus 1, where b is less than 100? We have 5 options here, a, b, c, d, e. So the important part here in this problem is it says we have integer leg lengths, and we have a right triangle. So we can draw a right triangle just to visualize this problem. So we have the side length to be a, another side length to be b, and the hypotenuse is b plus 1. So we can use the Pythagorean theorem. So we get a squared plus b squared is equal to b plus 1 squared. So over here, we know that, so if we expand b plus 1, we have b squared plus 2b plus 1. So we know that if we cancel out b squared from two sides, we have a squared equals 2b plus 1. And since b is an integer here, 2b plus 1 has to be a perfect square. So 2b plus 1 is a perfect square. And also b is less than 100, so 2b plus 1 is less than 2 times 100 plus 1, which is just 201. So that means a squared is less than 201, because a squared is equal to 2b plus 1, right? So if 2b plus 1 is less than 201, a squared is less than 201. So we should know the squares under 200, so we can just try them all out and see which one works. How much squares are there, firstly, that are less than 201? So we know that 14 squared is 196. So there are 14 squares, there are 14 possibilities for and positive integer a. However, do all these possibilities work? Let's try 196 for an example, just to make sure. So we have 2b plus 1 is equal to 196. When you subtract 1 from both sides, we have 2b is 195. So this definitely has a real solution. However, we want to look for a case where b is an integer. And if 2b is 195, so if 2b is 195, b is gonna be a decimal number with 0.5. So that doesn't work. So this actually applies to all of our integer even perfect squares. So 14 squared, 12 squared, 10 squared all don't work, because up to 2 squared, because if we had, so 2b plus 1 is an odd number, and the integer even squares are an even number, and even number can't be equal to an odd number. So the integer solutions don't work. So now we're basically left with 13. So all the odd solutions, 13, 11, 9, 7, 5, 3, and 1. So we're tempted to choose 1, 2, 3, 4, 5, 6, 7. We're tempted to choose B, and if we circle that, we're going to get the wrong answer. The reason here is because when A is 1, so just pay attention when you see really small values like 1 and 0 and 2. So when A is 1, we have 2b plus 1 is 1 squared, which is just 1, right? So 2b is going to be 0, so b is 0. This indeed is an integer solution. However, when b is 0, we don't have a length here. So the whole a, b plus 1 thing is not even a triangle. So this triangle, or this whatever segment, is not right triangle. Is not a right triangle. So b equals 1 and a equals 1 is, b equals 0 and a equals 1 is not a valid solution. So we'll have to cancel 1 out from our solution set. So the answer is going to be a equals 6. The answer is going to be a, 6. Because even if we try to figure out all these other solutions, the smallest answer here is just 6. So we can't So it proves that we can't eliminate any more options. So thanks for watching. The important part here is we firstly know that we have a right triangle, so we can use the Pythagorean theorem, and then we have integer length, so we made sure that 2b plus 1 is an odd number and it's also a perfect square, and then we eliminated a equals 1 because that makes b equals 0. So thanks, bye.